To the big data Quadfecta. I'm Brian O'Neill. I work for Health Market Science. I'm the lead architect there, and this is Taylor Goetz, the development lead. And we're going to be walking through our use case, why we chose the technologies we did and how we're applying them. And then we're actually going to do a deep dive on how we integrated Storm and Cassandra. So hopefully everybody will enjoy it. OK, so Quadfecta. I actually had to look that up. Because what had happened is, we lose the video there? I had done a blog post on a trifecta where we put Kafka, Elasticsearch, and Cassandra together. That seemed to be working well. And then we added to that Storm. So I didn't know what to call the new thing, so we said Quadfecta. Then when I looked it up, it ended up being an Urban Dictionary term that meant that the ping pong ball in beer pong lands on 4 cups simultaneously. So that sort of just stuck. So what we'll be doing is going through the 4 things that we think we got right and that are working well. So should I wait for the slides? Jokes. 2 peanuts go walking in a park, and 1 was assaulted. That's all I got. What do you got? You know?
I have nothing. Not after that.
There we go. OK, so there's the beer pong. So we'll pick up from there. All right. So, and continuing on that theme, sometimes I think big data these days is sort of in vogue, right? And there's a lot of hype around it, and it took us a lot of time to figure out what big data actually was, right? We figured, and we had heard that if we get big data, it'll solve all of our problems. It'll make coffee for us in the morning, and everything, right? But if you do some Googling and try and look for a definition, you'll eventually stumble upon the 3 V's. Sometimes there's 4. But we focus on the 3. The volume of data, variety of data, and the velocity, right? And all 3 of those have to play into our solution to service our customer demands. So now I'm going to go through our use case. So we work for Health Market Science, and what we do is we take thousands of these data feeds and we put them together into a master file. That's called master data management. So in our master file, we have every practitioner in the United States, every healthcare organizations, and then we affiliate all those different entities together over time. And that's important to a lot of different industries, one of which would be pharmacies. So when you go to the pharmacy and need to get your script, you hand your script to the person behind the counter, they actually have to figure out whether that doctor was eligible to prescribe you that drug before they give you something that's potentially illegal, right? So that one of the uses of our data is it would hit our data on the back end to figure out if that prescriber was actually eligible to do that. And the goal there is to eliminate a lot of the fraud, waste, and abuse in the system. Plus, in general, our customers use our data to gain a lot of insights into the space out there. So we do analytics on top of the data to figure out influencer networks, right? So if a physician is a critical person and his opinion counts, he may influence other physicians. So here are the details of our numbers. On the physician and practice side, we have about 6 million unique practitioners in our database. That's not too bad as a number size. But when you think about the 2,000 sources that we bring in that comprise the data, we maintain those 2,000 sources over time, over all time. So for compliance reasons, it's important for a pharmacy to be able to say, I allowed this prescription 6 months ago. Was that prescriber eligible 6 months ago to prescribe that? So we're not just keeping the current time, but any point in time, so that you can go and search this and find out what the characteristics of, and then what data contributed to that entity at that point in time. On the claims side, we also have, I think, the largest claims database out there. So anytime you submit a claims a claim for insurance, it's probably in our database, de-identified. But that's a lot of data. So on the claim side, we have 1 billion claims annually, and we maintain 5 years of that. So that's 5 billion. So the numbers get big. I think it's 9 or 10 terabytes on the claims data side, and then our physician is growing. So I forget what the number is there. So some of the challenges we deal with is that some of the data has schemas associated with it. Some is unstructured. We actually harvest data off the internet. So some of those 2,000 feeds come off the internet. And then in addition to that, those schemas change over time. So you might get an input from the government, a government agency that's maintaining state license information for practitioners, and 1 month it comes in with 6 columns, next month it comes in with 10 columns, right? And our database actually has to deal with that. So if you take a look, and what I'm going to be talking about is the platform that we've built, right? And here's where, I think when you put the technology stack together, you get a lot of powerful capabilities, right? So when you throw Storm and Elasticsearch and Cassandra and Kafka all together, you get a lot of these great capabilities, which allows you to deliver multiple products. So if you take the business needs at the top, right, we actually deliver all these different solutions with a single platform that can ingest the data, put it in a standard format, make it searchable like Google, right, and then answer all sorts of different questions. One of the things that we do as well is expense management. So a lot of the large pharmaceutical companies have to report out on how much they spend on each doctor, right? So the government can verify that they're not bribing doctors. So they'll hand us all of their expenses. It just goes right into the engine. We run it like anything else, and we can match it up against our master file and then output answers for them, right? And I think when you're architecting a system like that, the flexibility in the system is critical. We could have built one-off apps for each one of these business needs, but by building it as a platform, we can just basically take these 4 components, stitch them together, and now we have a new product and new offering. So that's really powerful. Okay, so just on the data center, I want to put this one out there because this is more of crowdsourcing. We have about 3/4 petabytes of raw storage, and we are entirely virtualized. We use VMware, and we have a SAN, right? All 3 of those characteristics were there before we chose Cassandra. So we ended up rolling out Cassandra onto this infrastructure. And we're looking at it now, and we're saying, should we have gone physical? Should we be going physical? We have no idea. There's been a lot of people talking today about, some people deploy out into Amazon's web services. Some people are running their own data center like we do. Data is obviously critical to us. So we absolutely run our own data center. It is on premise. But how we configure that data center is still up in the air. And I'd love if anybody has any kind of information related to physical versus virtual as far as feature, performance, and function compared to cost. I'd love to hear it. But that's our current approach. Okay, so if you look at the platform that we're about to describe on how we stitched everything together, this is what it is. Is everybody familiar with master data management? Has anybody heard that term, MDM? Hands? Okay, not a few. Okay, all right. So this is our version of MDM. On the left, we have data sources coming in, right? As I mentioned, some come in from the web. We go out and harvest information. So we have something called a harvester. It brings it in. We get data coming in from government sources. So sometimes, this is actually a CD coming in the mail, right? And we have to pull it in, load it, grab a flat file. And then also we have customer information, like I mentioned, the expenses. So when that comes into our system, that could be in any format, and it could change over time. We could put that CD in the drive, and suddenly they're using an Excel sheet, right? The government organization that maintains these oncologists just decided to use Excel instead of the text file that they were using. So we have to be really flexible. So what we do is we process that in the first set here. So we standardize and validate it. So we apply a layout to that data to add a bit of structure. But really at this layer, all we want to do is tag fields. So the data comes in whatever format we want, they want, and then we tag which columns what, right? We don't want to apply too much structure. We don't want to make it so that we can't flex to accommodate what kind of data is coming in. So at that point, we're just standardizing and validating, and then we push it into NoSQL, which is Cassandra right now. After that, right, we have to take these 2,000 streams of data and find out which ones are talking about the same thing, the same practitioner. Right? One might have an address, another one might have state license information. So we need to match it up and then consolidate it. So if these 100 streams all have data about the same doctor, they might have conflicting addresses. So we take that data in and we run it through pluggable rules, some logic that our data scientists figure out to figure out which of those addresses we should choose, right, and associated, and then we rank the addresses and put them on what we call the profile. So once we've done that, we can actually push it then into our index and our relational storage, right? So we've added quite a bit of structure at this point. We've consolidated all these data sources. We've picked what data we should use, and then we've pushed it, and now we can move on to analytics. So once we have that structure, we can run the analytics on top of the data, and we can present that data through dashboards and reports. We then allow our customers to interact with that through both the user interface and the web services. So that is master data management to us. And here's the crux of the problem, which is what drove us to choose Cassandra. And I mentioned this a little bit. We have multiple streams. So picture 1,000 of these, or a couple thousand of these arrows, right? All data streams coming in, right? And the F represents an entity and what I call fragments, right? So we get fragments of the entity that are split across streams. And they come in at different times. And then we have to associate them together through matching. Meanwhile, the schemas underneath of us might change. All right. So that was the use case quickly. Hopefully everybody captured that. And we're going to move on to the design. So we had a relational database at the base of our technology stack, right? So we have Oracle. You probably saw it in the other slide. We have Oracle RAC. We have a massive Oracle system. And what it meant to make this shift to big data for us was to swap out the system of record, which was Oracle and relational, and instead plug in Cassandra, right? So you saw from the design slide, the flow is different now. Cassandra is the first place we write to, and that is the single source of truth. Everything else is then derived from the data that's in Cassandra, right? So the relational database to us is really just another means of presenting, and actually exactly what it is it's one point in time. So as I mentioned, we store all points in time of all the data everywhere. That's in Cassandra. We then materialize a single point in time into Oracle so that people can view it. All right, so this is an important slide to me. One of the things that drove us to use Cassandra, in addition to the flexibility and the scalability, was that I think Cassandra nailed the primitives that you need. And I was asked earlier today, what was the hardest thing about getting to use Cassandra coming from a relational world? I mean, I come from a relational world where we had 180 relational databases, massive modeling, and lots of tables to deal with. And then I had to come to Cassandra, right? And you're tempted to apply the same kind of modeling techniques that you use in the relational world when you come over to Cassandra. And I said, it actually wasn't that big a shift if you just don't apply those relational concepts. Just ignore them, right? And you focus on this in the middle, right? Which is a map, right? A map of maps, basically. When you take a look at a column family, a row key is your first key into it, right? And that goes to another map, which is the columns themselves, which is a key, which could be a composite, which I'm representing with the array, that goes to a value. And if you just think of that, that's your data structure. Now use it to the best of your ability, and that thing can distribute across lots of different nodes. That's a really, really powerful concept, right? So once we had nailed the storage primitive, which I thought Cassandra did really well, what other primitives did we need to add to the system? Well, the one we needed was a queuing, right? So as we have all these streams coming in, some of them are dropping millions of records on our door in one day. Some of them are trickling in. We needed a queuing primitive, right? So we needed the push and the pop of a value, right? In addition to that, we also needed to be able to process these changes in the data and do something with them, right? So that's the emit and process of a tuple, right? And I think Storm nailed those primitives, right? And then finally, since Cassandra is mostly opaque and has no idea what kind of bytes you're putting into the system. It cannot apply any kind of smarts to that data, right? So at some point, you need to apply some smarts so that you can query this data quickly. And that's the index, right? The index field by type. And we do stuff like, our customers want to search for Dr. Bob Smith, right? Meanwhile, in our system, it's Robert Smith. So at what point did we know that Bob was really Robert? And that's where the index is smart enough to know that and can index the data properly. So when we take a look, we covered our distributed processing primitives with these 4 technologies. Okay, so along the way, and I think, if you look at themes and, building some earlier presentations today, idempotent operations, how many times have you heard that thing, that term today? 30, 50? Really important. It's as easy as, I shipped an operation to one node, I lost communication with that node, I have no idea whether it did it or not, so I need to put it over here and run it again, right? My system, my architecture, my design better be able to handle that case, right? And then in addition to that, Nathan Martz of Storm had a great little, what was that, Strata? He was at Strata? Has a great little presentation on immutable data, right? And we sort of switched, we adopted that model where your database is really just an assertion of fact at a time. Don't go change anything, don't do updates, don't do deletes, it's just assertions of facts at a point in time, right? And that makes idempotent operations a lot simpler, right? So, and then the anti-patterns to that is the transactions and lockings, just don't do it. So, one thing there, and I think there's an earlier presentation on Storm today, but this is important. You just told me that I have to be entirely idempotent, right? And there are certain anti-pattern, there are certain things that are hard to achievable with that kind of design, right? One of those is counting, right? So as things are happening, I'm trying to count. And if I replay something, I'm going to count it twice, right? So that's bad. So Nathan came up with an elegant hack, I'll call it, to try and to tolerate replays, but also allow counting and state transformation. And the way that he did it is, and somebody in the earlier presentation, they mentioned Trident as well. So if you take a look at Storm, and you'll get more into this, so I'll go quickly. What he did is the stream of data that's coming in, this doesn't just apply to Storm. You can actually implement this design in anything. You can batch it up, right? And you can actually parallelize all the processing of those data, but then when you go to update your state, you then sequence it, right? So here, if we have 3 batches of data that we want to process, and let's say we just want to compute a sum for each one of those batches. So the first batch is total of 4. I'm counting something. The second batch has 13 of those things in it. The batch number 3 has 13 of those things in it. Batch 2 has 6 of those things. Right? If I look at the state transformation as I go, provided I've sequenced those batches, right? When I process batch 1, I'll have a total of 4. When I process batch 3, I'm going to wait until I've processed batch 2. Right, and here you've brought everything back together, right? So that waits. 2 comes in, he adds his 6 to get to 10. Batch 3 can then apply, right, adding the 13, and then when the second batch gets there because it was a replay, I know I've already added it. Right, so that's a neat little hack to do state in a system that is mostly parallelized. Okay, here's what we did wrong. We got 2 of these slides. So, and this is not to knock Hadoop. I know there's a lot of Hadoop fans here. But we, as I said, switched to use Cassandra as our system of record, right? So we first load all raw data into Cassandra. It goes nowhere else. We do not load it to HDFS. That's it. So we were running our Hadoop jobs against Cassandra, and we found that to be incredibly inefficient. So I don't know if anybody, we've been trying to talk to as many people as possible here to find out if anybody's doing that successfully with Cassandra input, right? I know a lot of people, and we were in the first place, writing Cassandra using the output of a Hadoop job, but input, it wasn't working for us. So the kind of times that we were expecting to see were not there. So I'd be interested if anybody wants to talk after or just yell at me right now. All right. So in addition to that, we also needed to track what changed, right? In order to went into that next Hadoop job, we had to track what changed. So that added a layer of complexity that we didn't want. And we'll see how Storm fixed that for us. Okay, and this is what we did wrong, sort of. I'll put a sort of on this one. One of the reasons that we chose Cassandra in the first place is because of the cleanliness of the code. If you guys have been in there, Jonathan does an amazing job. That is a great code base. There's some legacy stuff is sort of like, super columns are still in there and things like that. But but it's a really great code base. And when we were looking at HBase versus Cassandra, we went down in the code and said, what could we do with this? Can we extend the functionality here? And the answer is yes, absolutely. It is very clean. I mean, when you saw Edward's talk earlier, if you're up there for introvert, you're able to just go in there and build on top of it, right? With just a few hours of getting oriented kind of thing, which is really neat. So maybe that's a bad thing when you want to go in there and you build your own trigger capability. So we weren't willing to wait, and we wanted this trigger capability because what we were seeing is lots of different clients accessing Cassandra, right, directly, and we knew we needed to maintain some wide rows, some indexes, so that people could get at the data through other dimensions. We did not want every client accessing Cassandra to have to know about those different dimensions, right? And we hadn't gotten to the point where Eric was saying that everything went through a nice common service-oriented architecture API yet, right? So we implemented our own trigger functionality. It's out there. You can go to GitHub, go to Cassandra triggers. I do not recommend doing this, but you could. So it worked well initially, and to be honest, it's actually still in production right now. It's been there for a year. It's doing well, but what happened is we started leveraging that too much. So, we said, we need one more wide row, we need one other thing, and then our entire business process was starting to be articulated via trigger, right? So, that we started to get this, sick feeling in our stomachs that, our business process should not be a side effect of writing to Cassandra, right? That's not good. Okay. What we did right. We did eventually look at REST APIs, right? And I think if you were in Edward's talk earlier, we wrote Virgil, which is a REST layer on top of Cassandra. And then we got it, right? Okay, everything's got to go through services and API. That's a really smart thing to do. Let's do that. So we put Virgil out there too. You can go and you can use it. It's actually working. Again, ours is in production. It's been in production for a long time. But I'm really excited about what we saw about introvert, right? So if you want that HTTP and REST capability, but you also want to be able to plug in and do your own thing, introvert looks like it's going to be a really powerful thing to use. Okay, so I spent a lot of time. How am I doing on time? Oh man, okay, I'll go faster. Okay, so Kafka is great. I think a lot of people have heard lots of good things. Way better than JMS. We were using ActiveMQ and Oracle Advanced Messaging, Advanced Queuing, and they topple over once you start flooding them with messages. So we took a look at Kafka and it fitted into the architecture, as I'll show in a few slides. Likewise with Elasticsearch, we actually, 2 years ago, we're doing the comparison between Elasticsearch and Solr, and at that point we figured Solr was the way to go because Elasticsearch was too young. But if you've tried to scale Solr, you know that it can be a bear, right? You're doing master-slave kind of relationships and directing queries to certain nodes and then updates to others. It's not very pleasant. So when Elasticsearch incorporated it and became a little bit mature, we took another look at it and said that's the way to go. I'm going to leave talking about Storm to Taylor. But basically, as I said before, it offers the primitives that we needed for distributed processing. And it has become our backbone, right? So I think some of the questions around polyglot persistence are how do I manage and control the data flow from one system to another? When you're using, we've got, this is not the only thing. We've got MySQL databases and Oracle databases, and we've got Elasticsearch, and we've got Cassandra. So we need to control that data flow and make sure that all the systems get updated appropriately, right? So that's become Storm to us. But the interesting thing there is, and I still long for the day when everything was a trigger, is that all CRUD operations now have to go through this data flow, right? So I'll just go quickly through the system that we have. We have a REST API that you hit, and it queues the data into Kafka, right? Then the Storm topology reads that off, right? And we have a bunch of Cassandra bolts that Taylor will go into. They write to Cassandra multiple times, right? Also to keep the wide rows and everything up to date. And then we dump it into Elasticsearch so that it's also googly, right? So the great thing here is that, we talk about high availability, and as long as you've done everything, in an idempotent fashion, right? You can tolerate things going down. Right? So if you lose part of your Storm topology, no problem. Storm will reroute, replay the tuple someplace else. It'll get run, right? If you lose a node in your Cassandra ring, no problem. You've got a replication factor there, right? If you lose all of Storm for some time period, no problem. Or if something was going wrong in your system, no problem. Just rewind your offset in Kafka, right? So all of these things played really well with one another, right? We were really happy when it all came together. Just real quick, so what's coming next? We have a desperate need for a graph database. As I mentioned, we maintain all these affiliations between all these entities, all the practitioners, how they relate to one another, and all the organizations. So, we're going to look at Titan, and I'm looking for anybody that has experience running Titan against Cassandra. Awesome, we'll talk. Okay, so we were looking at Neo4j, but obviously it'd be better if we could manage just one persistence mechanism. All right, I'm going to leave this to you, right? You've got slides for this.
Okay.
And then here's Taylor. Taylor's the author of Storm Cassandra, so go for it.
Okay, how many people here have heard of Storm? Awesome. Is anyone using it? Great. I'm going to go into a little bit of a discussion of how we use Storm and some of the open source software that we've developed for Storm. Storm is a real-time distributed computation system. So what that means is it processes data in real time, and that contrasts with a batch system like Hadoop, where you have a clear start and end to jobs. In Storm, your computations are open-ended. They run forever. One of the things that Brian mentioned with Hadoop was that for a while, we used Hadoop to do some of our batch processing. But we also found out that we needed to react to data in real time. So in some cases, we may get data dropped, and that gets dropped as a batch. So we could have a Hadoop job that would deal with inputting that data into our system of record. But then we also wanted to support real-time data coming in. So what we were finding was we were writing the same logic in two places, one for a Hadoop job and one for a real-time system. So one of the things we figured out, or we thought about, was what if we treat all data as real-time input? And that's where Storm sort of came in. So what does a Storm cluster look like? This is actually a diagram of one of our development clusters. But Storm has an architecture very similar to Hadoop. There's Nimbus, which is the master node. That takes care of assigning tasks out to the worker nodes. Zookeeper is used for cluster coordination. Storm actually doesn't do a whole lot of writing to Zookeeper, so it's pretty easy on your Zookeeper cluster. And then supervisors are your worker nodes. And they're the ones that actually run the tasks that operate on your data. And in our development environment, this is not I wouldn't suggest a cluster like this in production. This is what we use for a small development environment to test applications in a clustered environment. In a production environment, we probably wouldn't co-locate Storm and Cassandra, and we'd have a multi-node Zookeeper cluster. Storm primitives. At the highest levels, the main primitive in Storm is streams, and streams are just an unbounded sequence of tuples. Tuples are just key value pairs like a hash map. The next primitive is a spout, and a spout emits streams of tuples. Bolts are your unit of computation. That's actually where you do your operations on tuples, do calculations, that sort of thing. And then if you combine bolts, spouts, and streams, they come together in what's called a topology. A topology is a combination of any number of spouts and bolts and defines your overall computation. So to dive in a little deeper with Storm spouts, they, as I mentioned before, represent a stream of data that can be queues, like Kafka, JMS, Kestrel, Twitter Firehose, sensor data, weather, that sort of thing. And spouts emit tuples into the topology. Bolts receive tuples from spouts or other bolts and operate or react to that data. They can perform functions, filters, joins, aggregations, and in some cases, database writes and lookups, and we'll get into more of that a little later. And they can also optionally emit additional tuples. Storm topologies define the computation of your application, and it's a data flow between spouts and bolts. Parallelism of components. So when I say a spout or a bolt, those operate as tasks in your topology. And tasks can be parallelized, so they can be fanned out across multiple nodes in your cluster. And what groupings do are define how that data routes to individual tasks. So for example, if you're doing something like counting words, you want the same word to always go to the same task running your bolt. So you would use a grouping that allows that to happen. Here's a sample of what a topology might look like. You have a spout attached to some sort of a real-time data source, and it emits streams of tuples to the bolts, and the bolts perform your computation. Storm and Cassandra. So the main use case is being able to write Storm tuple data to Cassandra. For example, the results of your computation or pre-compute indices, and read data from Cassandra and emit Storm tuples. That enables you to do dynamic lookups and that sort of thing. And I'll show a couple use cases in a few minutes. The Storm Cassandra project that Brian mentioned on GitHub started a little over a year ago. Basically, what it boils down to, is we have several components, Storm components that are bolts, and they're also Trident functions. And if I have time, I'll talk a little bit about Trident later. But we have these generic Cassandra bolts, one that allows you to write to Cassandra and one that allows you to look up. The writing Cassandra bolt is available in both batching and non-batching. The batching one, what it will do is as tuples stream in, it will batch them up and attempt a batch mutation all at once. So I mentioned that it provides generic Storm components, and then what you actually plug in, the custom piece that you write, is called a tuple mapper and a columns mapper. And that defines the interaction between the Storm tuple and the Cassandra database in either direction. So a tuple mapper tells the Cassandra bolt how to write a tuple to an arbitrary data model. So your data model can be anything you want. All you really need to do is define that interface. So given a Storm tuple, it will map to a column family, map to your row key, and then map that data into Cassandra columns. And the columns mapper interface does the exact opposite. It tells Cassandra, the Cassandra lookup bolt, how to transform a Cassandra row into a Storm tuple. The current state of the project, we are on 0.4.0, and that should be released soon. Maybe tonight, depending on if I go to the drink up or not. We're using the Astyanax client. For a while, we were using both Astyanax and Hector, and allowed you to switch that at runtime. But when we started looking at supporting composite keys and composite column names, it became a lot easier to settle on a single client. We chose Astyanax at that point. It comes with several out-of-the-box mapper implementations. So basic key value columns, like a hash map, valueless columns. I'll show you an example of a use case that uses that. We have a counter column implementation that was a community contribution. We allow lookup by row key and range query, and as I mentioned, composite key and column support. And we're also, we've introduced Trident support. Future plans, we plan to switch to CQL and enhance our Trident support. So a couple examples. So persistent word count, if those of you who are familiar with Storm, one of the first sample projects you go through is the word count. So, and there's an example of this in the GitHub project that you can run. But basically, what we have is a word spout that uses a field grouping, and that field grouping makes sure that all the same tuples, all the same words essentially go to the same bolt, the count bolt, and then we use a shuffle grouping to the Cassandra bolt, which actually receives the counts and then writes them into Cassandra. Another interesting feature of Storm is DrPC. So I've talked about how you can parallelize and horizontally scale your topologies. What DrPC does is take that power and it adds a DrPC server, a specialized spout and a specialized bolt that does the coordination. So what you can do is create a DrPC client that will create a query, and that query gets parallelized out into your topology. And then using transactional mechanisms, it will actually return you a response, so you get all the power of a Storm topology with essentially remote procedure call. One example of that is the reach computation. So if we define reach, for example, as, let's use Twitter as an example. So if I tweet out a URL, and then I have X number of followers, and each one of those has followers, the reach is the total number of people that have been exposed to that URL. So let's say we are Twitter and we have massive amounts of users and followers and a huge graph. So what you can do with Storm and DrPC and our Cassandra implementation is break that down into several simpler functions that we can then parallelize. So in this example, we have a DrPC spout that's just going to receive a URL. The URL is our query. We want to find out how many users have been exposed to that. That gets passed down to a Cassandra bolt, and that Cassandra bolt sitting on top of a wide row valueless column. And the row key to that is just the URL, and then the values, well, it's valueless, but the values are the users who have tweeted that. So what that does is then emits the URL and the user for each one of those and sends it to the followers bolt. What the followers bolt does is takes the user that it receives, for each user it receives, it looks that up and emits all the followers of that individual user. So now we've fanned that out, and we pass it on. We do a fields grouping based on the ID and the follower, and that goes to a partial uniquer bolt, which gathers up partial batches of counts, and then finally to a count aggregator. And just like that, it returns your result. And it can scale horizontally. That's my time. This is a notional topology. This is not what our MDM solution looks like, but this gives you some idea of how we're using Storm. I mentioned earlier that we treat all incoming data as real-time data. So when we do batches, we read that data and write it to a Kafka queue. And real-time data also comes in the same way. There is some transformation. It goes into a Kafka queue and then enters one of our topologies. So we have topology implementations for loading, standardizing, matching, and consolidation. And they all write to Cassandra, which is our system of record. And then in addition to that, they also handle all the polyglot persistence operations, like writing to Elasticsearch, writing to a graph database. And then finally, for reporting, what we do is we have processes that take the system of record data out and store it in a relational database that we can report off of and also use for delivery for people who have purchased our product. This is a small subset of the previous one. This is an example of what part of our loading process looks like. So we have entity fragments coming in, and you can think of an entity fragment as a smaller piece of a larger entity. So it might be address information or state license information. So fragments come in, they're written to Kafka. We use a transactional Kafka spout to route that into the topology. There are a couple things going on here. We shuffle that so we can parallelize amongst multiple fragment functions there. And the several streams come out of the fragment function that we group by, for example, fragment ID and entity ID. We do that so we can maintain counts and do analytics kind of things. One simple count would be the number of fragments we have per entity, the total number of entities processed, the total number of fragments processed. And that goes to a persistent aggregate function, and those counts through a Trident state implementation get written to Cassandra. Then we also route another stream to a Cassandra lookup function, and what that does is does sort of reference table lookups to enhance the data, and then it goes to a Cassandra write function, writes it to Cassandra, and then passes on downstream additional standardized match, that sort of thing. Some shameless shout outs. Our GitHub accounts, HMS is currently where Storm Cassandra, Storm Elasticsearch, and Storm JDBI, which should be coming soon, is, and a couple of projects on my GitHub account. And with that, we may have a minute or two for questions. All right.
Was that comprehensive? Just one more note, if we can go back here real quick. So we were talking, some of the things I think it is an evolving, it's an evolving area how to best integrate Cassandra with Storm, I think. And though, we've got this function out there, the exact composition of the topologies, I think, is something that we don't yet have patterns for. So if you take a look at this topology, there are multiple, in some of our topologies, there are multiple write functions, right? So we write to Cassandra here, we write to Cassandra here, we write to Cassandra there. One of the patterns we've been evaluating is whether you actually construct the mutation as you go through the topology and do one single write. at the end, right? And that takes advantage of some of 1.2's ACID properties for the mutation, so that you can get, you can eliminate a little of that eventual in the consistency, so that when you write this thing, all the indexes there immediately.
So I guess in the past you've been like using a custom trigger implementation to update Elasticsearch? Would that have been
Actually, we did.
Yes.
Yep.
replacing that?
Yes.
Okay.
Yep. Yeah, and that's what I mean. It's like and I vacillate some days between like everything is now in Storm. Thou shalt go through the data flow for every CRUD operation. I come in and that gives you some sanity some days, and other days I'm like, no, that's terrible because now I got to go through the data flow for every CRUD operation.
There are definitely trade-offs to all everywhere. There are trade-offs. The index solution it didn't scale for us from a business standpoint, but now you could argue that we're doing everything through Storm. That involves a lot of network traffic, but in general, Storm is extremely performant in that area.
Anything special for the Nimbus? The Nimbus is essential.
I'm sorry, I missed the question.
Do we do anything special for the Nimbus? Care and feeding?
Like, well, I mean, it's not like Cassandra. Cassandra's, there's no single point to it.
Oh, because Nimbus is essentially like the master?
Yes.
Basically, with Storm, you have master, which is responsible for assigning work out to the nodes, and then you have supervisors. Both of those we run, and it's standard practice to run those under supervision. They're designed to fail fast, so if they go down, they can be picked up. So if Nimbus goes down, it'll come back up. If you lose the machine that Nimbus is running on, then your topology will continue to flow and work, but if Nimbus is down and you lose one of your workers, then Nimbus won't be able to assign another worker to that node.
Yeah, so we run it under supervision. The processing doesn't flow when it crashes, right? But you got to get it back up before other stuff crashes. Okay. Otherwise, flow will stop. Yeah.
Okay.
Thanks.
Oh.
Good.
About Kafka, is there a way to make it fault tolerant?
Fault tolerant. Good.
You mean in what sense?
Make sure not to lose data that transitions through Kafka, you lose the machine.
My understanding is that that's coming up. There is replication, and you can operate them as a cluster, and you get some partitioning, but I believe, I'd have to look at the current version of Kafka. I think that's coming up in a new version that provides some enhanced fault tolerance.
But it is in the works?
Yeah.
I believe so.
Yep.
What do you do in terms of code deployment? I mean, given the fact that everything's real time, right?
Yeah. Yep. Yeah, it's a great point.
Storm topologies, basically, they get packaged up as a jar file, a fat jar file, not unlike what you do with Hadoop. And they get submitted to the cluster, and Nimbus will pass out the jar file to all the workers. As far as redeploying,
Yeah.
changes for rules
Yep.
would be a redeployment of your topology.
Well, yeah, in some
But
cases.
in some cases, but you can build in, you can do anything you want in a bolt or spout, so you could build in some sort of, something like that. There's also another project that we had up on GitHub is Storm Signals, and what that lets you do is send out-of-band signals to components of your topology so they can essentially communicate with one another.
Yeah, so I guess in the previous presentation, and we've done the same thing, we have a bolt in our world. We have a bolt, so as tuples are flowing through the system, as the data is flowing through, we have a bolt that we call the processing engine that actually calls out to Ruby. it hands the tuple to the Ruby script. The Ruby can do whatever the hell it wants to transform the data, do anything, and then it hands it back. That thing loads the Ruby from a URL, so we can replace the logic at runtime, right, out from underneath of it. It has a 5-minute expiration, so if we update the Ruby, it'll clear its cache, pull the new Ruby in, and the new logic will take effect immediately. And in the earlier presentation, they were using Drools for the same thing. So if you embed the Drools library into a bolt, you can run Drools and make decision off of Drools rules in your filtering and stuff. So.
Where do you get throttling and prioritization?
What was that?
Throttling and prioritization.
Throttling.
In Storm?
Yep.
Yeah. Depending on what your topologies are doing, especially with Kafka, it's very easy to overload certain systems. For example, Kafka could probably outperform writing to an Oracle database. So what you can tell Storm to do is, Storm has guaranteed processing. So you can say a tuple must pass through the entire bolt tree before it gets acknowledged if it doesn't replay it. When you're using that type of topology, what you can do is say, limit the number of outstanding tuples to X number. And then Storm will hold back until all those tuples have been acknowledged.
Yep. Yeah, we should say that Storm is a pull model. So when the spouts are implemented, Storm asks the spout for new data when Storm is ready to accept new data. So it can actually throttle itself based on, it's called a max spout pending. So it's built in. All right.
Okay, I think we have to wrap up.
Yep, we'll be available if anybody wants to talk. It's our favorite subject.
Okay.
All right.
Thank you.